Hello again, it is me, Derek from Tomcat Gas Training, and welcome to this video all about these little things. Now, as usual, before we get into this video, please could you take some time to subscribe because it helps my channel, and again, don't forget to hit that notification bell because you want YouTube to tell you when we're uploading videos, and I'm sure you know by now it's Mondays and Wednesdays. Also, don't forget to give us that thumbs up, and then why don't you share it with your friends? Anyway, that's all the waffle and spiel over and done with, so let's get on with it and find out what these are. Now, this little thing here is a thermoelectric device, and this little thing here is a thermocouple. So what we're going to do is we're going to find out how these two things work in conjunction with each other, where we will find these things, and how they work. So, like I've just said, let's get on with it, and let's first of all find out where we're going to find these. Now, this is the fire we're going to be removing the thermoelectric out of, but let's just quickly look at the devices what operates the thermoelectric. So this is what we call the ribbon burner. So the reason why it's a ribbon burner is because it burns from here, where it goes into the burner, down this little section here, and then across to the thermocouple, which is here. Now, this actual ribbon burner also makes up another safety device using this thermocouple. So you can see the flame burns across here into the thermocouple. So this is what we call the ASD. So when the room becomes vitiated meaning lack of oxygen, the pilot flame will lift off, cool down the thermocouple and knock the gas off. So this occurs as the concentrations of the carbon dioxide, or the CO2, in the combustion air reaches 1.5 or 2%. And the corresponding carbon monoxide CO concentrations reaches levels of round about 200 parts per million, which is within safety limits really. So like I say, it will then lift the flame off because the flame will be looking for the oxygen, so it'll bend upwards, cool down the thermocouple and knock off the gas. Now let's have a quick look at this thermocouple itself. So this is a thermocouple out of a boiler, but is pretty much the same principle. So basically what we've got here is the tip of the thermocouple, which goes into the flame, a copper wire, and inside this copper wire is like an electric wire, which is connected to this insulated end here. So this is the hot tip and this is cold. The heat doesn't transfer down here. What we've got here is two dissimilar metals which create an electric current. And Thomas Seebeck invented this, which is called the Seebeck effect. And he founded this in 1821, believe it or not. So basically what he came up with was two dissimilar metals add heat will create an electric current. So what metals is this end made up of? Well, it could be nickel chromium, it could be iron, or it could be copper, or it could be constantan. Now, constantan is a copper-nickel alloy. So that's what the two dissimilar metals could be in the end, which creates this electric current, which creates about 12 to 30 millivolts DC. On average, these make about 50 millivolts DC to keep a boiler thermoelectric device open. So like I say, you add the heat to the end here, it creates electric current which goes around the end of there, and then that goes to the end of the thermoelectric device, creates this a small electric current which holds open the electron magnet, which keeps the safety device open. So why do we need this thermocouple? Well, because the thermocouple is part of the flame supervision device, kind of does two things. So it stops the gas flow to the burners when a fault or a risk has occurred. So whether it's blown the gas out or whether we've got vitiation. And it is also to ensure the safe ignition of the gas burner by preventing quantities of unignited gas from building up before it ignites. So this is the old way of your flame supervision device. We use flame rectification now in boilers rather than thermocouples. Now, before we move on to the rest of the components here, let's find out exactly how we can test to see whether these thermocouples are working okay. Now, you can actually test a thermocouple electrically. So what I've done here is I've set myself a little test rig up. So I've got my multimeter here, and you can see I've set it to 200 millivolts DC. And I've got my standard 2 probes, so my black connected to the common, and this is to the live. Now this would have been better if I had crocodile clips, but I don't have crocodile clips. But it's only a test and an experiment. So I've got my blow lamp here again, which is a bit fierce for this, but there's only me on my own, so what I'm going to do is just light it and make sure the thermocouple is in the flame, which it looks like it is, just into the flame. And then I get my black lead and I put that onto the copper somewhere. So I put it on the copper, and then I use my red onto the end of there, and I should be getting a millivolt reading. So getting 18. So you can see it's glowing, and if I turn that off now, as this cools down, we should also be getting a reading of it going down. So you can see 28, 27, 26, 25. So we can see this thermocouple works perfectly. And like I say, it would be better if I had crocodile clips, but I haven't. So that's how you could test the thermocouple to see if it's working. That's if you've got a vice and all the other bits. Anyway, testing the thermocouple. So that's how we test a thermocouple. Let's see all the other components we have on this part assembly. This is the igniter. So when I press the button in, you can see it's igniting. So we need to light the burner. So first of all, this is the control knob. This is in the off position. So we need to turn it to ignition, and you'll notice I can push the knob inwards, and that means I'm overriding the safety device. When I take out the thermoelectric, you'll see what that knob actually does. So let's flip it over onto its front. So this is, if we turn it on the side on so you can see it, this is the thermoelectric device in here. So this is where the thermocouple connects to it. So first of all, we need to disconnect the thermocouple off here. So I'm just using a little adjustable spanner to just undo that knot. And that's removed now the thermocouple. So it now leaves the thermoelectric. Need to make the adjustable spanner a bit bigger. We just need to undo the outer case. And now this is the thermoelectric. So that is where the thermocouple goes onto and makes this electricity, this millivolts DC, to open this thermoelectric device, which is electromagnet. Now, if I hold this close up to the camera now, I don't know whether you're going to be able to see this, but if I press the button in, can you actually see that when you press the knob in, it lifts, makes that plunger come inwards. And what the plunger does is it pushes against that. That means you're holding it on there for 10 seconds, and then when you let go with the knob, that's supposed to stay there because the thermocouple is creating electricity to hold it on. So it's not strong enough to push it down. It's only strong enough, this millivolts DC, to hold it on. And then once the thermocouple cools down, out it pops. So that's how we get it out of the fire. Let's actually see this in action. Now let's see this actually working in action. So here's our thermoelectric device. So what I've done is, out of this old burner for a fire, an insect live fuel effect fire, I've taken out the thermoelectric out the back, which just connects around the other side. What I'm going to do is I'm going to use my blow lamp and just heat up the thermocouple. I'm then going to place the thermoelectric into its cup, push down the plunger like you would do when you're pressing the button down, and then let go, and it should stay where it is, and then the thermocouple should cool down and the thermoelectric should pop back up. Shall we try it? So let's light the blow lamp first. So we only need a low flame. So I'm just going to heat the flame up. I'm going to place the thermoelectric in, press it down, take away the heat. So you can see now I've just done exactly what you would do when you push the button in on the gas fire. And then we would have 60 seconds where this would need to pop up. Right on cue. So that's what it looks like when it's actually working. Now let's have a look at the ASD working, or the atmospheric sensing device. So if I turn the pilot on, just by, again, pressing the knob down is overriding the safety device. We're now heating up in through the ribbon burner into the thermocouple. I've now left it open for 10 seconds and it's kept open the thermoelectric device, which is allowing the gas then through to the burners. So if I take down this here, which is the linterester, this is where the pilot gets its air in for combustion. So this is its pre-air, so pre-air through this hole, post-air around here. So if I block off that hole, you can see the flame has lifted off and we've got vitiation because there's no pre-air on it, post-air. So if I block that off, you can see it's lifted over the thermocouple. Now, if I wanted to test the thermoelectric device in this, what I can do is I can blow out the pilot flame. I will hear the gas coming out, I will hear the thermoelectric knock off, and there should be no gas going to that because the thermoelectric's slammed shut. Now it does say in the training manuals you can do this by just turning the gas off, but then you don't know whether the gas that is coming through or the thermoelectric is passing. So if I blow this out, I would start a stopwatch and listen for this click. So let's listen for the click. There you go. Now, since 2000, the year 2000, when space heaters have been manufactured, all thermocouples, whether it's in a boiler, a cooker or a fire, will knock off or should knock off within 60 seconds. But pre-2000, this could actually go up to 180 seconds. We'll finish off in a minute by looking at the chart, what all the times are for thermocouples or thermoelectric devices to knock off. So we've just tested the thermoelectric to see whether it's passing. So let's test the ASD now. So if I turn it back on, and I couldn't hear any gas before, so I knew it wasn't passing. Now I could actually stick my finger on there and lift it off, or I can use this flat bladed screwdriver and just block off the flame going to the thermocouple, and again we'll wait for it to knock off. Okay, so it knocked off. Now, we've just proved the pilot flame had knocked off. This would have actually kept the burner running because the flame, the ribbon burner flame, is still going into the burner. So if I just, this is where it'll get hot. Not for you, for me. So if I put this fire on full rate, I'm just going to go back a bit. I'm going to block off the pilot flame going to the thermocouple again without burning my face off. And let's see if it knocks it off while the fire is actually running on full. And it still knocked it off even though the fire was running at full rate. So that's how the thermoelectric and the ASD work in conjunction with this fire. So if you do have a fire where it has the ribbon burner and the flame is burning horizontal, not vertical, then you've got an ASD. Now we've just tested this ASD, or the ODS, oxygen depletion system, whichever you want to call it. But the manufacturers don't always give you times for them to knock out. So we've just covered over the pilot flame going to the thermocouple to see if it knocks out, and we've also stuck our finger over the inlet hole to make it vitiate. But if the manufacturer hasn't given us a time for the ASD to knock out, then we're only really relying on the thermocouple timing. Don't make your own tests up, because a lot of the time these are really hard to do. This is dead easy to do on this fire, that's why I've picked it. But there are some appliances where you really struggle. In those cases you're just blowing out the pilot flame and listening for the click, or turning the gas off and listening for the click, as the training manuals say. So don't make up your own tests, but it is good to actually see them knock out. Now, as promised, let's have a look at these times behind me to see how long the thermoelectric devices should be knocking out within pre-2000. Because remember, post-2000, every one of them now should be knocking off within 60 seconds. Let's have a look then. So if we start off at the top, central heating boiler, maximum heat input of 70 kilowatt net is 60 seconds. So that's always been 60 seconds. Next one is cookers. The oven is 60 seconds, but the hot plate or griddle is 90 seconds. Space heater, so if it's a radiant fire, within 180 seconds. Decorative fuel effect gas appliances, 60 seconds. Warm air heaters, maximum input 60 kilowatts gross, 60 seconds. Storage water heaters, less than 35 and equal to 35 kilowatt net, 60 seconds. Greater than 35 kilowatts to equal to and less than 70 kilowatt net, 45 seconds. And finally, combination boilers and multi-point water heaters is 60 seconds. There is a note here down at the bottom. It says, for cookers, the gas valve should shut down within 60 seconds if the burner is situated in a compartment, or the oven, and within 90 seconds in the case of an open burner, covered burner, or griddle. So that is the time, remember, for post 2000, and all of them now should shut down within 60 seconds. Now that is the end of the video of these little things. And as usual, if you've liked this video, why don't you give me that thumbs up? And if you haven't liked it, give us a double thumbs down because it makes it extra doubly rubbish. But if you're not subscribed to my channel, then please subscribe because it helps the channel. And don't forget to hit that notification bell because you want YouTube to tell you when we're uploading videos. I'm not telling you it's Mondays and Wednesdays. Anyway, all I've got left is say yous. Thanks for listening, thanks for watching, and I'll catch you on the next one, guys. Cheers.